Hi everyone, here's a quick homework guide. Question 1 is about rescaling a vector to be a different length without changing the direction that it's facing in. So let's pretend I have a vector that goes over 4 and up 6, this vector, and I wanted to scale it to be half as long. It makes sense that if I was dividing it into two vectors, so this vector would be one that points in the same direction as half as long, I can get that by going over by half the amount and up by half the amount twice. So the point of this picture is if I want to rescale my vector, I can rescale the x and the y separately. So if I want my vector to be half as long, I can take my x displacement and divide it in half, and my y displacement and divide it in half. And the resulting diagonal vector will also be half as long. So in problem 1a, I said we've got a vector 1, 5, and we want a vector that points in that same direction but is unit length. So it's a length of 1. Well, first let's figure out how long is that one. So it's going to be 1 squared plus 5 squared, which is 26. So this is root 26. So all I need to do is I need to scale each of my directions down, or equivalently my entire vector down by a factor of root 26. So that's easily achieved by multiplying on the outside by 1 over root 26. And so now this is a new vector that's still pointing in the same direction, but I've shortened it, I've scaled it down by that factor. And if you wanted to, this is the same thing as if you sort of distributed this into the two sides. So 1 over root 26, 5 over root 26. That would also be okay as an answer. Part B asks, what if we want a vector pointing in the same direction only with a length of 10 instead of with a length of 1? Well, let's just do this in two steps. I know that this one is length root 26. Step 1 is let's scale it down to be length 1. That's this vector. And then once it's length 1, I know that I can take that and multiply it to scale it up to be whatever size I want it to be. So if I just take the answer from part A and multiply it by 10, now I know its length has to be 10 because its length used to be 1. So that's a great answer for that question. All right, so I've got someone at negative 3, 10, and they are going to walk along a vector that I defined in a polar way. So the vector is length 3, and it's at a 30-degree angle. And they're walking at 3 feet per second. And let's define a vector v that is the vector from wherever they're ending up at a particular time all the way over to the point 100, 100. So that's v. And then this could be, you could think about this point as a position vector going from 0, 0. All right, and then this would be vector a because it's a vector that points from the origin to wherever person A ends up after a certain amount of time. Okay, so the question is find v. So what I know is that the a vector plus the v vector equals 100, 100. I can see that visually. So that means my v vector must be 100, 100 minus my a vector. All right, so let's figure out what a rectangular representation for my a vector would be, because then I can just subtract the components. So a is going to be, let's see, where's my starting spot? So negative 3, 10. And then I've defined my motion in a polar form, but let's go ahead and redefine it in rectangular form. So let's figure out what's a vector that points in that direction. I'll break this little triangle out down here. So this is 30 degrees, this is 3. And what I really want to know is this x and y, because that would be the two components of my rectangular representation. So I know that y is going to be equal to 3 times the sine of 30. And this is going to be equal to 3 times cosine 30. And the reason why we went over in class way back when we first did this, which is if you think about SOHCAHTOA, so sine of this angle is that divided by that. So if you write down that equation and then isolate y, you'll get this. So sine of 30 is 1/2, so that's 3 over 2. Cosine of 30 degrees, should be degrees, is root 3 over 2, so that's 3 root 3 over 2. Great, so now I've got time scaling a vector that is, oh, sorry, I'm writing this backwards. That's 3 root 3 over 2 and 3 halves. And you might pause here to think, wait a minute, is this vector the right length for the speed my person needs to be going? But the answer is yes, because we calculated these two lengths assuming the hypotenuse was 3, which would be 3 feet per second, because this is the length that gets added to the position once per second. All right, so we've got 100 and 100, we've got our A vector, so now we can find the V vector just by subtracting them component-wise. So I'm going to do that right now. I've got, for my X component, 100 minus both of these parts. So I'm subtracting -3 plus 3 root 3 over 2t. So I distributed the t into here. And then for my Y components, I've got 100 minus 10 plus 3 over 2t. All right, so there's my V vector. The next part asks me, what is an equation that tells me the magnitude of V as a function of time? So I know I can find the magnitude by using the Pythagorean theorem on the X and the Y components. It seems worthwhile to me to simplify this one step before we do that, because if we're just about to square some stuff, I want the things that we're squaring to be as simple as possible. So 100 minus 3 is 103 plus 3 root 3 over 2t. And then here I've got 100 minus 10, so that's 90. And then, ooh, did I make a mistake here? So this should be a minus sign, because I'm subtracting that amount. Okay, so then minus 3 halves t. Okay, so this is the simplified version of the V vector. So now I know that this thing is going to be the root of the X part and the Y part each squared. So 103 minus this, and then 90 minus that. And before going ahead and expanding these and trying to simplify any further, it's worthwhile checking what do we want to use this for, because maybe we don't need to simplify it any further. Okay, so now it's saying use Desmos to find the place where the length of the vector V is at its minimum. So this is telling me the length of the vector V. So let's go ahead and just type this into Desmos and figure out where is that at its minimum. All right, here's Desmos. So what was I doing? I was saying V as a function of time is going to be the square root of something squared plus something else squared. I like to get the template in first before I type my function, just because it helps me make sure that everything matches up properly. So 3 square root 3 divided by 2 times time. And then this is 90 minus 3 over 2t. Okay, cool. I don't see anything because my scale is too small. Ah, there we go. So pretty clearly it looks like this is the point where we've got a minimum. So I'm going to go ahead and write these values down. It looks like the t value that produces the minimum is 44.734, and the value of v at that time is 26.442. So it's important to think about what do each of those numbers represent. So the x-coordinate is really our t-coordinate, so that's the time at which the v vector is at its smallest, and then this is the actual length of that vector, the 26 number. So then the last part of this question says, use your answer from part C to find the position of the person when they're closest to 100, 100. Vector v is the vector that points from the person to that point. So in part C, we just found when is that vector at its shortest. And so that must be the time when the person is closest to that point. So now I need to figure out, all right, how can I figure out where person A is? That was the very first equation that we started with. Remember, A of t was person A's position after a certain amount of time. So all we really need to do is plug in the time that we just found with Desmos right there, and it's going to tell us what are the x and y components. Desmos works perfectly well as a regular calculator, not just a graphing calculator, so I think I'll use that. So for the horizontal component, I've got -3 plus t, which is 44.734 times 3 square root 3 over 2. So that should be the x position. And the y position should be what? It should be 10 plus 3 over 2 times that same time. So that should be the y position. Okay, question 3 was from the exit ticket. So I asked you about this time-changing polar vector equation where the distance is t plus 50 and the angle varies with time. And I got a couple of interesting different results. So some people thought that this plus 50 was shifting the entire spiral over by 50. So it was centered at 50, 0 if we were thinking in a rectangular way. Some people thought that it shifted it up, but I notice here that even though we're starting at like 0, 50, it's not that the spiral is centered at that point. It still seems like it's wrapping around the origin, so that's different. Some people thought that it dilates the spiral by 50, so presumably we're still at the origin, it's just that everything's kind of larger by 50. And then some people said that it adds 50 to all the distances, so the spiral starts at 50, 0, but it's still going around the origin. So let's redo the problem ourselves just to think about it. If this is my vector, where this is the distance from the origin at this particular angle, I can imagine a couple of times where the angle would correspond to 0, 45, 90, 135, and then some distances. So at 0, I'm going to go out a distance of 50. So definitely we're starting sort of here. And then when I'm at this angle, I'm going out by 95, which is not quite twice as far, so something like about there. And then when I'm at 90 degrees, I'm going out by 140, which is not quite 3 times as far. So let's see, 1, 2, 3, so like about out here. And then 135 is going to be sort of out there. So it does seem like it's making a spiral that's probably going to go around this way like that. So the correct answer was D, the student who said that this is just adding 50 to all the distances. And I think the key to realize is that the distances aren't talking about an x distance. It's not talking about a y distance. It's talking about a distance from the origin along the line at a particular angle. So the distances are always measured starting from the origin. And that's a good way of understanding why the first one isn't correct. Why the third one isn't correct. So this one isn't correct because here the distances are all spiraling out from a point that's not the origin. But the thing that's creating the spiral is the fact that we've got distances that are all positive that go out from the origin as the starting point. That's what makes the origin be the center of the spiral. So this sort of doesn't really make sense for shifting the whole thing over. This one doesn't make sense because this would predict that at an angle of 90 degrees, the distance would be 50, but clearly from our table that was wrong. The prediction that said that it was dilating the spiral by 50, it's not really dilating it by 50 because then it's like every distance should have to be 50 times what it would have been otherwise. So if we had 50 times t, that would be dilating it. As far as the extension goes, let me just say a couple words about that. So let's say we wanted to come up with an equation that was a spiral centered here. We should be skeptical that this is going to turn out easily using a polar representation. Because like I said, the whole point of polar is that everything is relative to the origin. In particular, the distances that we're traveling are relative to the origin. So the idea that we would have something centered over here is an intrinsically rectangular idea because we're interested in shifting an x coordinate by 50. But nothing in our polar representation cleanly corresponds to an x or a y. It's a totally different way of thinking. It corresponds to a distance and an angle. So does that mean it's impossible? No, definitely not. It's just that it's not you can't easily think about it using polar. So one thing we could do is let's use what we've learned about rectangular. So let's say we want to start here, but then have a spiral motion going out of that point. So we could have two vectors. We could have a vector that's constant, and this is a rectangular form of the vector that starts us at 50, 0. Then we want a parametrically defined vector, again, sort of rectangular way of representing, that would take us in a spiral. So what would take us in a spiral? I know cosine t sine t would define a circular motion. If we scaled that by a particular number out here, like 2 or 3, that would dilate the whole circle. If we dilated it by a factor of t, now as time's increasing, the size of our circle's increasing, and that would produce a spiral motion. So if I add those two separate types of motion together, the constant starting place plus this dilating spiral, that's going to give us this kind of shape. So this is already an equation that would produce that overall kind of form. And if we wanted to, we could simplify it by combining the x component and the y component, and then we could rewrite it back in polar form. But that's obviously going to be really messy. What I wanted you to take away from this was just all of that thinking that I said, realizing why it doesn't naturally fit with a polar way of thinking, realizing that you could still write an equation for it using rectangular, and realizing that, again, if you needed to, you could convert that back to polar. The details about how to do that are less important to me right now than the underlying conceptual flexibility of realizing what these different ways of representing vectors are good for. Okay, let's do the last one before the extending ones. So I was just reminding you that you can define vectors like this, where x and y vary separately as functions of time, and this is just our simple parameterization of a parabola that we did way back when we were doing parametric equations. So with that thought in our heads, I said, let's say that person A is walking along a path like this that's defined by y equals root x with a horizontal speed of 1 foot per second. So that means that even though they're changing both vertically and horizontally, this part of their position, that length, is changing at a speed of 1 foot per second. Meanwhile, person B is way out here at 110, and they're walking towards the origin at a speed of 10 feet per second. So this speed is 1 foot per second. Okay, so let's try and capture all of these information, capture all of this information as vectors. Let's do person A to start with. So person A, I know, starts at the origin, and I can just use a simple parameterization of the square root function, where the x component is time and the y component is the square root of time. And I know that this will define that path. Then I need to ask myself, okay, is the speed that person A is supposed to be moving at actually correct if this is the path they're following? And it seems like the answer is yes, because from 0 seconds to 1 second, this defines their horizontal position, and I can see that that's going to go from 0 to 1. So I know that their horizontal motion is 1 foot per second. Cool, so that's person A. Let's do person B. Person B is starting at 110, and now they're moving along a vector in a particular direction. So let's kind of figure out where that vector is pointing. I know that it's pointing from here to the origin. So I could actually think about it as like a single super long vector, which then I'm going to scale back to be the speed that I want them to be traveling at. So if I was thinking about this as a super long vector, the x component would be negative 100, and it's negative because I'm imagining starting at 100 going back to the origin. So negative 100, and then the y component would be negative 10 because I'm starting at 10 going back to the origin. Okay, but if I just left it like this, person B is going to go from their starting place to the origin in 1 second. And you can see that by imagining, okay, if t is 0, this entire vector is their starting place. If t is 1, now I've got 100 minus 100 and 10 minus 10, which is the origin. So in other words, when t goes from 0 to 1, I go all the way back to the origin. So what I want to do is, this goes all the way back to problem number 1 from the homework. I just want to take this vector and rescale it to be shorter. So I want to divide it by its own length, so that way it'll be a length of 1, and then I'll multiply it by 10. So let's see, its own length is 100 squared plus 10 squared, so square root of that, which is the same thing as, let's see, 10,100. Is that right? Yeah, that makes sense. Okay, so that's what I want to divide it by. So root 10,100, and then I want to multiply it by 10 to scale it back up. Cool, so that's a great equation for b. And now I want vector v to be the vector that points from A to B. So what that means is that A plus vector v equals vector b. So v is going to be b minus a. We've done this, 100 times now. So let's go ahead and subtract a from b, and I'm going to do it component-wise again. So I've got the b vector is 100 plus that thing. So 100 minus, let's see, 100 times 10 is 1,000 over root 10,100 t. Did I multiply all that correctly? Great. And then from that, I'm subtracting another t that comes from a. And now for the y components, I've got 10 minus 100, because that's 10 times 10, over root 10,100 times time. And then from that, I'm subtracting root t. Cool. And there we go. And now if we wanted to, we could use that to answer a bunch of other questions about the times at which there are different distances from each other and the angles and all that. Okay, I hope that this